The wave function of a pair of entangled particles in general is the sum of products of the eigenstates for the two particles. And the net result is that the two particles, or in particular two electrons in the helium atom, are intimately correlated in their behaviors. Contrary to many popular opinions, the particles do not need to be identical particles. In my experiments with photons, one of them was green and one of them was violet. So they do not need to be at all identical. And particles that have never interacted can be independent, but particles that have interacted will remain entangled. So, we go on. What is non-local? Okay, within a helium atom, the two electrons are intimately interacting with each other. So it seems hardly surprising at all to expect them to be, their behaviors to be correlated. Both Einstein and Schrödinger independently noticed that a peculiar feature of quantum entanglement, that the entanglement persisted no matter how far apart you took the two particles. This bothered both of them very deeply. They couldn't understand how their intimate correlations persisted when they were so far apart. There's no way they could possibly interact. Einstein, Podolsky, and Rosen, in a very famous paper in 1935, proposed that quantum mechanics was an incomplete theory. And in order to explain entanglement, we proposed hidden variables within quantum mechanics to explain these non-local entanglements. Following Einstein, Podolsky, and Rosen, Schrödinger and Curie suggested a modification to quantum mechanics in which entanglement just simply disappears when the two particles are very far apart. However, that hypothesis changes the predictions, and everybody at that point believed the predictions in quantum mechanics were perfect. No one was willing to admit or even to think about the possibility that would give incorrect predictions. Niels Bohr argued against Einstein, Podolsky, and Rosen, and said that the hidden variables were unnecessary. Okay. So pointing out, the spectrum of helium was required entanglement. You couldn't get it correctly without this. But most people said, "See, that's quite sufficient. We're convinced. Well, all you need is convince us with helium." And before my work with my associates, the Gosler, Horn, Shimoni work in 1969, that was quite sufficient for people to be convinced that quantum mechanics always made the correct predictions. Nobody before then suggested actually doing an experiment to test it. Actually, nobody could think of one, except Bowman and Harriman were unique. In 1957, they showed that the Wu-Shaknov experiment refuted the Schrödinger-Curie hypothesis that I mentioned earlier, that entanglements disappeared for large separating particles. Next question, what is a Bell inequality? There are actually three, there are a number more, but three important ones that I was involved with. 1964 was actually the first one. That was John Bell's inequality, and it's of great importance. It showed that Einstein, Podolsky, Rosen's argument led to exactly the opposite conclusion that they had come to in their 1935 paper. But Bell did not actually make any new experimental predictions. Like everybody else, he assumed the predictions of quantum mechanics would be incorrect, or were always correct. So, in 1969, my friends Mike Horn, Amber Shimoni, Dick Holt, and I proposed a new inequality, the CHSH, and I will describe it in a moment. And we made the heretical proposal to actually test whether or not this rather bizarre prediction from quantum mechanics was true. And we developed, proposed an experiment where we found a significant loophole. I'll discuss that in a minute. And finally, in 1974, Mike Horn and I went further and produced a loophole-free example and further produced what we call local realism. So let's go back to 1964. John Bell's, okay, they assumed that quantum mechanics, everybody assumed that the quantum mechanics made correct predictions between the correlation of separated particles. And Bell, with great irony, showed EPR's argument led to the opposite conclusion, that the EPR's discussion of entanglement implied incompatibility between the predictions of quantum mechanics and EPR's local hidden variables. He showed the intimately correlated behaviors cannot be explained by the introduction of EPR's hidden variables. Unfortunately, his 1964 inequality requires that at some point the two particles must have perfect correlation. But as Ben Franklin pointed out, the only thing for certain in nature is definite taxes. So that can't occur here. Such an experiment, perfect correlations exist. There's always going to be something wrong. And so his assumption it was too restrictive and you couldn't test his inequality. So in 1969, we all looked at that and realized that his assumption was not necessary. We could derive a new inequality. That's called the CHSH inequality. That doesn't require perfect correlation at some point. And we proposed the total heresy of suggesting that an experiment should be done. And we designed the experiment, all the necessary details for it, and we have the first actual testable Bell inequality. And we now have two theories. CHSH inequality is one theory, and quantum mechanics is a second theory. Gee, we have two different predictions. How about we let nature tell us which one is true? Do an experiment and see which one gives the correct results. Could be in either one, for all we know. Nobody had ever done this before. So, unfortunately, the perfect, even then, doing a perfect experiment was not quite possible with the technology we had. So, but we found essentially some very simple supplementary assumptions that allowed us to do the experiment. I might point out that great care must be taken in normalizing the probabilities. Change the slide, sorry. Okay. So, the third inequality was produced by Mike Horn and me in 1974. We were trying very carefully to understand what the inequalities really restricted. And in the process, we came up with local realism. Local realism is an extremely general, very inclusive theory. Indeed, it underlines virtually all of Einstein's space-time approach for doing physics. It's a very significant generalization of Einstein and also Rosen's local hidden variable theories. For these theories, we produce a new inequality, the CH inequality. It allows loophole-free experimental tests. The CH inequality actually reduces the CH-SH inequality if you apply a very simple, even simpler assumptions that we had CH-SH had. And at the time, in '74, it was too difficult to do that experiment, but recently technology has improved significantly, and in 2013 and 2015, conclusive experiments have actually been done. So, since I was intimately involved in this, and I realized just how important this was, to determine whether or not Einstein's whole plan of attack on physics was correct, I actually decided I really wanted to do the first experiment to test it. So, in 1972, Stuart Friedman and I performed and published the first experimental test of local hidden variable theories. And thereby we demonstrated that non-local quantum entanglement is real. This is the first time anybody had ever done an experiment that would violate the Bell inequality. Then I did a second experiment in 1976 to repeating that with a different source. I'll get on to do that. And another experiment after that to actually look at the circular polarization. And in 1974, in between these, I did another experiment that's not really related, only peripherally related to Bell inequality experiments. The demonstrated the first particle-like behavior of photons. To demonstrate a real wave-particle duality for photons. Okay, here's a picture of the first experiment. This was done by Stuart Friedman and I. This is a very young Stuart Friedman standing at the right end of the experiment. This was done at the University of California in Berkeley. We published the results in '72. This was Stuart Friedman's PhD thesis project at Cal. We measured the polarization correlation, the linear polarization correlation of photon pairs that were emitted in a three-level cascade in calcium. Singlet S0, singlet U1, singlet S0 states. Total angular momentum is conserved. The two photons are entangled. In order to generate that state, we had to excite calcium. Calcium is very corrosive. You can't put it in a bulb. We had to have it in an atomic beam in the center. The operator there is an atomic beam apparatus with calcium and pain in the neck to keep going, all the vacuum pumps leaking oil all over the floor, a real mess. We had, now, one of the things that made it really difficult was that tunable lasers had not been invented yet. So everybody else subsequently uses tunable lasers. We didn't have them. Steve Chu was down the hall trying to build one. It took him an extra 2 or 3 years just to get his working. So we decided we could do it with a deuterium discharge lamp filtered, but it's a very weak excitation. Experiments took a long time. The good news, with a very slow count rate, is that we did not need to subtract any accidental background. So we got 6.3 sigma violation of the CHSH inequality. And we use the protocols that the CHSH had dropped. Okay, so simultaneously with that, Dick Holt, he was the last agent of CHSH, he and Frank Biscuit at Harvard were doing a parallel experiment. They actually got their results slightly before we got ours, and they said, got the opposite result. We showed the quantum mechanics was correct and hidden variables were excluded. They found the opposite result. They didn't believe the result. So they never published it. They waited until we had published ours and decided not to publish. But nonetheless, there it was. This got me very worried. Okay, well, maybe I did something wrong. Sue and I might have made a mistake. So I readapted, spent a lot of time with Nick Holt, explained to me how he built his sources. Mercury vapor inside a bulb, the electron beam, it actually was a cathode ray tube electron gun we used. I was working on this alone. And I had to use separated isotopes of mercury, any odd nuclear spin in mercury. Mercury's got 5 or 6 isotopes. You got to use, so I had found some mercury 202, microscopic amount that was sufficient, and built actually a whole series of electron guns, and violated CHSH inequality by 4.1 sigma. And again, used the same earlier protocols. And while I was at it, I put in quarter wave plates, and switched to a linear polarization to a circular polarization, and measured the circular polarization. All in perfect agreement. Okay, in between those two, I did another experiment to test for the particle-like behavior of photons. Curiously, nobody had ever experimentally done that before. Way back in 1917, Einstein had predicted, in order for a gas of molecules or atoms to come to thermal equilibrium with a Planck black body spectrum at the same temperature, that photons had to be emitted and absorbed and stimulated emission with what they call directional energy bundles. What were they? Well, they're now called photons. But it wasn't obvious exactly what they were, or were they really particle-like? Schrödinger looked at that, and he had an idea. Suppose you have a classical wave packet propagating out, and it hits a half-cylinder mirror. Classical Maxwell's equations will show half of it going transmitted and half of it reflected. On the other hand, if you have real particles, it will go one way or the other. It won't go both. So, Schrödinger proposed a following experiment. Suppose you put 2 photomultiplier tubes on opposite sides of a half-cylinder mirror. Then, if particles behave like, photons behave like particles, you will never see coincidences on either side of the mirror, half-cylinder mirror. If this air behaves like a simple wave, it will be sometimes partially transmitted and partially reflected, and you will see coincidences. So he went down from Vienna to Budapest to his experimentalist friend Hennessy in Budapest and proposed doing the experiment. They did it in 1955. Unfortunately, they didn't have single photon sources, and they grossly misestimated the detection efficiency, and their experiment was inconclusive. So, in 1974, between the two Bell's theorem experiments, I didn't actually do that experiment, but to try to do it in a fully conclusive way using single photon sources. So I actually ended up using the same source, mercury source, that I used in the other experiment, and I did it twice. Oops. Okay, so here in the middle, okay, in the middle you have a source, and you have B splitters on both sides. And this is 2 photons are coming out, and I perform this beam splitter trick on both the first and the second photon of the entangled pair of photons. And I use some recently discovered mathematics produced by Glauber, where he's studying fluctuating classical electromagnetic fields, and applied the Cauchy-Schwarz inequality to that, and found an amazing result that the two anomalous, say if you had photons were not particles, they were always waves, like Glauber's theory suggested, then you would see particle coincidences on each side of the beam splitter. Whereas if they're particles, you would not see. So the product of the two possible coincidence rates beside the beam splitters, I found that product, according to Glauber's theory, the product of those two had to be greater than the actual cascade photon rates we're seeing all the time. So I actually measured that, and I found no anomalous coincidences. Part of the photons were definitely behaving like real particles. Okay, so we move on to the next part of the theory. Mike Horn and I were trying to understand what does Bell's original result and the CHSH result actually constrain. It was a lot more, we found it was a lot more than just Einstein, Podolsky, Rosen's hidden variable theories. And then later on, Abner Shimoni and John Bell had an additional discussion of this in a series of papers. And so perhaps you should call it the Glauber-Horn, Shimoni-Bell local realism. What we invented essentially a new theory. Mike Horn and I originally called it objective local theories, but it got renamed local realism. What is local realism? It's a very general theory. It's a significant extension of Einstein, Podolsky, Rosen's hidden variable theories. Okay, and it allows loophole-free tests, what we couldn't do with CHSH. We did not require causality, as we did not require particle-like behavior. Unfortunately, it was very short-lived. It was actually dead before it was born, because it had already been refuted by the Friedmann-Glauser experiment back in 1972. So even though it was dead on arrival, since it was the CH inequality provided a loophole-free test of both local realism and hidden variables, people began to work on it. So, what is local realism? What does it assume? It's actually so natural. Anton Zeilinger, one of my co-laureates, he once noticed that if Bell's theorem had first been discovered before quantum mechanics, it was so reasonable it which has immediately been adopted as a law of nature. It assumes nature is made out of stuff. Everyday matter, objects. Objects have intrinsic properties. We don't even need to know what the stuff is. Whatever it is, we assume that it exists and it's distributed throughout space. Einstein and also wrote called it elements of reality. John Bell called it local fields. Cosmologists call it matter. The Bible calls it light mingled with firmament. It's been around for a long time, this whole idea. We call it objects, objectively existing stuff, objective reality. Objects, what is characterized as an object? It's something you can localize and put in a box, like a pair of shoes, or maybe an electron, or a solar system. You have a very big box. It's simpler than other theories. General relativity goes much further. It says whatever the stuff is, it has a finite mass energy density. We don't require that. It just has to be there. Other theories require deterministic evolution. We don't care. It could have a totally stochastic evolution, totally random. The present does not uniquely define the future. It could be non-deterministic. All we assume is whatever this stuff is, we don't know, it's got intrinsic properties, and then the properties of the stuff determine not the results, but just the probabilities of the results of an experiment you perform on the stuff. And if you have a different experiment you perform on it, presumably you're going to get a different result. It will depend upon the characteristics of your experiment, if you have adjustable parameters. And we further eliminate some other nonsense, like Schrodinger's cat. Schrodinger introduced his cat as a reduction to absurdity. Unfortunately, people started assuming that absurd was true. We assume Schrodinger's cat is either dead or alive. We haven't looked at it yet. We just don't know which. That the result is truly definite. Okay, I mentioned stuff you can put in a box. Well, what's a box? A box is a closed surface. Gauss, a marvelous theorem, I don't really know how he did it, but he showed that closed surfaces exist that divide space into two independent regions called an inside and an outside. Here I have two boxes. Here on the lower left, I have two boxes, Gaussian surfaces, if you prefer. They contain a signal source. Nowadays, the two characters inside the boxes are called Alice and Bob. This was back in 1976, before Alice had her trans operations, I guess. So, anyway, sorry for the gender shift. But, okay, so inside the box, we're doing an experiment. It has an adjustable parameter. And during some time interval, it measures something, we don't know what, and it gets a binary result, yes, no. Same thing's true. So what locality assumes is that the parameter setting in one box does not affect the outcome in the other box. That's the locality assumption. Okay, and that's okay, in these four-dimensional boxes, they're shrinking at the speed of light. And so on the right hand is the space-time diagram showing the shrinkage. Okay, any correlation has to have originated back in the overlap region. So, what does localism predict? Suppose we got these two boxes, and we further assume that the parameter choice in one box doesn't affect the outcome in the other box. That's Einstein locality. Okay, that's eliminating Einstein's spooky action at a distance. So, the great surprise, those assumptions are all you need in order to create, to derive the CH inequality. Okay. When we did this in 1974, the technology to actually test this did not exist. Without relying on the auxiliary assumptions. But since then, technology has improved quite dramatically, in particular on the quantum efficiency of photodetectors. And in 2013, two groups, one Anton Zeilinger's group in Vienna, and Paul Kwiat's group in Urbana-Champaign, Illinois University, had tested this. They first did it where the two boxes were not space-like separated, but they again repeated it with them space-like separated in 2015. In both cases, they found a violation of the CH inequality. So, local realism is dead. What does this say? Our first simple application, what's the simplest object you could describe? The simplest possible object consistent with my definition is a single bit of information. It's definable. Okay? We would like to believe you could put a bit in a box, especially if that box happens to be a personal computer sitting on your desk. Question: do there exist quantum mechanical objects that you cannot put in a box? Now is death of local realism limits? The answer is yes. It's called a quantum bit or a qubit. You're all probably working on making qubits right here. So this simple feature of local realism describes is all you need to get quantum encryption and other quantum features. We move on to some more recent work that I've done. Okay, so more recently I have discovered what was really at issue in the Bohr-Einstein debates over the BPR configurations. And it's what I call Born's ambiguity. It has to do with the difference between configuration space and laboratory space. And it's been an ignored elephant in the room. It's been hiding in plain sight for over 80 years. What is the ambiguity? Remember, I mentioned at the beginning, Schrödinger had two different equations. One that described hydrogen, and the second one that described helium, and the second one produced entanglement. Nobody seems to have noticed until I did recently that these two equations are formulated in very different spaces. That's the elephant hiding in the room. And the spaces are improperly linked by what I will refer to as Born's ambiguity. And this elephant's been hiding in plain sight now for 80 years. Okay, what is the elephant? Okay, EPR debate, I assert, has never really been settled. Has fostered two totally independent schools of thought. And these two schools of thought persist today. Surprisingly, they coexist, and nobody seems to have noticed until I did this recently. Local realism and quantum entanglement now bring to light the difference between these two schools. And surprisingly, the two schools of quantum mechanics are incompatible. One of them, first school, is actually a form of local realism, and as we just noticed, all of the effort that's been done, local realism is dead. It describes, the reason it's dead is it cannot describe, first school of thought cannot describe entangled systems. So, what happened? The two schools had each produced a series of textbooks. Okay, the first, some of you have been trained on one group of these textbooks. Some of you have been trained on other group of textbooks. You walk out of this room, I expect you'll be chatting with your friend. Gee, which one did you study from? Oh, gee, I was school number one. Oh, no. Okay. What's the first school? It's the earliest I could discover was by Born, 1933, 1935. That was in German. And the 1969 English translation was a slightly different name. Dickey and Whitney, a very great book that I used at Caltech. Dickey was at Princeton, who's there. Eisberg, 61. People used to call it quantum mechanics modern physics in the old days. Isley, okay, Feynman's review article from 1948 talks about a space-time approach to non-relativistic quantum mechanics. And his subsequent book, Feynman and His, Quantum Mechanics and Path Integrals, essentially echoes all of that. French, used this when I was a sophomore at Caltech, Principles of Modern Physics. Great book, and he updated it, French and Taylor, used at MIT in 1978. Another great book, Merzbacher's Quantum Mechanics textbook, 1961, two editions. And one of the granddaddies was Schiff, Quantum Mechanics in 1955. That's school number one. It formulates quantum mechanics in what I call laboratory space. What is laboratory space? Okay, it's the three-dimensional space that we live in. This room has three and only three dimensions, x, y, and z, which if I specify the x for a given coordinate system, if I specify x, y, and z, that uniquely specifies a point in this room or in your laboratory. Space has three dimensions and only three visible dimensions. And a very important feature of the space is it doesn't require any systems within it. It exists on its own, without any particles, without anything being studied. It has important geometric properties we have studied. All vector analysis, Green's theorem, Gauss's theorem, Stokes' theorem, all of these apply rigorously in laboratory space. This is geometry. So we have a unique point specified by a position vector. Okay, so what is school number one? Schrodinger's wave function, psi lab, is a function of the position in space. And there's a probability density, psi star psi, which describes, okay, the comparatives described are definable at every point in the lab. Depend upon this position in the lab. In general, they're different everywhere in the lab. The psi lab in school number one is similar to other, the wave function is similar to other classical fields, like electric field, the magnetic field, the pressure field, the air for sound waves, the wave heights for ocean waves. The evolution of the wave function is described by Schrodinger's equation operating in lab space. It describes, you've heard many people describe quantum mechanics as having probability waves propagating in space. It also has, if you multiply the probability density times psi star psi times particle mass, and you have a beam of particles, that gives you essentially the mass density of the beam at any given point in the beam. The lab space formulation also allows for what's called, Bohr calls the conserved probability curve. It's written up in all the various quantum mechanics textbooks, including some of those in the second school. Okay, the probability current flows like a fluid. And in fact, the authors of the various books all describe it as flowing like a fluid. One little problem with school number one. It only works for single particle systems. It cannot describe entanglement. Therefore, it is inviolable as a general description of or perfectly general description. Okay, let's move on to school number two. As some of you also have studied out of the books. One of the most important ones is by Beta and Salpeter, Quantum Mechanics of 1 and 2 electron systems. Study all the details of the hydrogen and helium spectrum, including all the quantum electrodynamic effects, compares them all with experiment done in 1957. Bjorken and Drell, okay, these are all the self-admitted applied quantum mechanics textbooks, if you will. Bjorken and Drell, relativistic quantum mechanics, does this relativistically. Quantum and shortly do this for multi-electron atoms, much bigger than helium. Dirac's book, first beginning of relativistic quantum mechanics. Landau and Lifshitz. Landau was a student of Bohr. Very famous 2-volume set, My Messiah, Quantum Mechanics. All done in configuration space, except the discussions of the classical limit and scattering theory. There he kind of flip-flops and has to revert to lab space. Pauling and Wilson, this is what all the chemists used for quantum mechanics, and the granddaddy of them all was Mathematical Foundations of Quantum Mechanics by John von Neumann, 1935. Okay, what is configuration space? All of these books formulate quantum mechanics configuration space. It's as an abstract, fictitious mathematical space with k dimensions, or k can be a large number. It's a vector space. It's used for specifying the configuration of a general dynamical system. It was originally introduced for Hamilton-Jacobi classical mechanics. And John von Neumann's book is famous in that it generalized the configuration space into what's called Hilbert space. Hilbert was his von Neumann's thesis professor. So, unlike lab space, its structure of configuration space depends on the system under study. Remember, lab space, you can put anything in it. Space was there with or without systems. Configuration space is very, very different. It depends on the system that you're studying. Number of degrees of freedom of the system depend on the system under study. Okay. So, what is quantum mechanics in the second school of thought? This is what I would call the Bohr von Neumann school of thought. From all these second group of textbooks. There, the wave function depends on degrees of freedom. First, psi config this is straight out of von Neumann's book. The various Q's are the degrees of freedom. So in the Schrodinger's equation, the second school of thought describes the evolution of psi config in this abstract mathematical space. So if you have a system of, say, two mobile particles, like you do in helium, then the arguments of psi config are position vector for particle 1, so an xyz for particle 1, and an xyz for particle 2. Wait a minute. We now have more than 3 dimensions. We have 6 dimensions. We can even add spin variables in there. Okay, the second formula comes out of York and Drell. But remember, lab space has 3 and only 3 dimensions. So this is very different space. So, importantly, psi config does not depend upon the lab space vector. In fact, there's no specific point in the lab where it is going to be evaluated. And if you did add it, then it would really be bad, because it would be essentially a hidden variable. And it's forbidden by what's called transformation theory. We could talk about coordinate space representations in quantum mechanics, momentum space representations, all kinds of fancy mathematical tricks we use would be prohibited. So if it's the same everywhere, has the same value everywhere in the lab, independent of the lab space vector, that means there are no probability waves propagating in the lab. And there is no conserved probability current.
I think you have to wrap up.
Sorry?
You have to wrap up.
Okay. So, yeah, I'm almost done. So, what Born's ambiguity? I thought I had, okay. Sorry. So, Born's ambiguity is claimed in his textbook that these two wave functions, the two argument spaces are the same. They are clearly not the same. They are not equivalent. So there are no probability waves. And so, more importantly, you would expect the n particle wave function would reduce to the single particle wave function for n equal 1. It doesn't. So, configuration space is required if you want entanglement. If you want to be consistent, you've got to use the same space for all descriptions. So therefore, you're stuck with configuration space. He's totally self-consistent. So lab space. So why are we having to go to this problem? Lab space formulation is essentially a form of local realism, and it's dead. Now, configuration space has its own problems. It's not relativistically invariant, pointed out by von Neumann. You can't build a conserved currents. So, there are also conceptual difficulties. That you can't have any waves. So, I haven't the faintest idea, by the way, what is a wave propagating in configuration space. I don't know. It's a mathematical, abstract concept. You can't have conserved currents either. Okay, so since I run out of time, I will quit. But basically, this observation is what was the debate between Bohr and Einstein. The two men were actually just talking past each other. Bohr was assuming quantum mechanics is formulated in configuration space. Einstein was assuming quantum mechanics is formulated in lab space. Configuration space is an artificial, abstract mathematical space. There are no prohibitions for faster than light propagation of signals, because there are no signals in configuration space. So all of Einstein's arguments carry no weight at all for configuration. And similarly, von Neumann's measurement problem, wave function collapse, disappears in configuration space. So I will skip the problem, but an apparent or final problem is, how does one unify quantum mechanics and general relativity without somehow formulating general relativity in configuration space? Okay, I will quit.
Thank you so much.